So we start the intro to quantum mechanics by talking about by reviewing or talking about the properties of waves, the equations of a basic plane wave, of a sine wave, right, of a single frequency sine wave, and the superposition of waves, adding two waves, and the fact that when you add two or more waves, depending on how they add, you get a envelope term and an oscillating term, and right, so you might get something. This is the envelope, and here, let me draw an axis, and this is the actual wave. Whoops, that wasn't drawn terribly well. But that when you add up waves, you start to get complex waveforms. That's the superposition of waves. That basic stuff about wave mechanics. And that leads us into quantum mechanics because one of the end results of quantum mechanics is that we can treat waves like particles, photons, and we can treat particles like waves, typically small things like electrons. So it's important to understand the properties of waves for quantum mechanics. Okay, so where does the intro to quantum mechanics, it comes from? Now let's take a step back and say the justification of quantum mechanics, right? That's the second huge contribution of Einstein, is the development of quantum mechanics. Of course, many people participated in the development of quantum mechanics, but Einstein was one of the first to get the ball rolling. But it all starts with, again, back in 1900, that there are these things that are not understood, right? The things that are not understood that can't be explained by classical physics. So those phenomena that that weren't understood, that required quantum mechanics in order to understand, were line spectra, the idea that you had discrete quanta, discrete lines of light, that just discrete colors of light that were emitted by a pure gas that was an excited pure gas, for example. Or if you look at a star and you look at the spectrum, you actually only get certain colors, not all colors. Line spectra, black body radiation, which of course we are looking at right now in advanced lab. So I probably don't need to go into much more detail than that. But the quantum, remember the what wasn't understood, the thing that wasn't understood was the intensity versus wavelength graph. If you experimentally, it looks something like that. But if you try to describe it with classical physics, you never get anything but that. And so it required quantum mechanics. It required discretizing the possible modes of oscillation of atoms in a solid, and the fact that they couldn't just oscillate, they couldn't just vibrate at any frequency. And that's what brought this down to allow it to go to zero instead of to infinity. Black body radiation, that was required for quantum mechanics, or quantum mechanics was required to understand that. The photoelectric effect, is really what Einstein is famous for. That's what Einstein won a Nobel Prize for, and that was understanding this idea that when you shine light on a metal, you get out electrons. That was understood long before Einstein, but that phenomenon. But the fact that people couldn't understand why, when you change the brightness of the light, you don't get more energetic electrons coming off the metal. You just get more electrons. You don't get more energetic electrons when you change the brightness of the light. But if you change the frequency of the light, the color of the light, you get more or less energetic electrons coming off the metal. So that says that the color of light has to do with the energy of the light. That is a quantum mechanical effect. That's the photoelectric effect. Okay, so then the Compton effect was this experiment done by Compton, where you can bounce light off of electrons, but it acts like a billiard ball bounce, right? It acts like two particles. And so this solidified, the Compton effect solidified the concept of the photon, light as a photon, light as a particle. This idea that you could treat light as a wave or as a particle, Compton effect. And that was also the photoelectric effect was indirectly required the idea that light is a particle. But the Compton effect sort of solidified that idea. And for each of these, I'm not writing down any equations because it's sort of one basic equation that represents the quantum mechanical aspect of each of these. And you can just look at it on the equation sheet or look it up or whatever. They're very much, to some extent, other than derivations, a lot of them are sort of just more plug and chug kind of things. So Compton effect, let's see. Is there anything else? I think those are the primary, concepts that allow us to justify quantum mechanics. The fact that things come in discrete quantities. That's the whole idea here. Things come in discrete quantities, not always continuous quantities. And what that then does is brings us to the next chapter in this story, and literally the next chapter in the book that we use, and that is now looking at the model of the atom. The model of the atom had to change once quantum mechanics was understood, and we start with the plum pudding model of the atom, and then the nucleus is discovered, and so now we've got the orbital radius, the planetary orbit model of the atom, and then people realize that classical planetary orbit model doesn't work because the electrons that are orbiting the nucleus would crash into the nucleus in tiny amounts of time. There's no way for them to stay in those orbits. And then there's the quantized orbits Bohr model of the atom, where he says, oh, they don't crash into the nucleus, they stay in these quantized orbits. So that's a concept of quantum mechanics, but doesn't explain why until we come back to this concept of waves, the fact that the electron can be treated as a wave. And so then the electron, can be treated as, or you can see the wave-like properties of any particle when you look close enough. So in an atom, an electron actually acts like a wave. It's got a de Broglie wavelength, and it actually interferes with itself as it orbits, essentially. It's not really orbiting, but as it orbits the nucleus, or who knows what it's doing. And so it's got more probable places that it's going to be in less probable places because of this concept of interference, right, of a wave. That's one of those properties of the waves that we should understand. Interference, constructive interference versus destructive interference. And so that has only allowable quantized orbits. And in the end, then Schrödinger, who sort of develops the classical model of quantum mechanics beyond Einstein, the one that you've learned about in Physics 302, ends up with a model of the electron cloud, because the electron isn't really in one particular orbit at one particular place. It's got probability of being in certain places at certain times. And so the final model is the electron cloud around the hard nucleus. So those are the models of the atom that we studied. So the basic bottom line, quantum mechanics that really allowed us. So just going back and saying, that really the takeaways of quantum mechanics is that energy is quantized. Energy is quantized, and for example, for a photon, Planck's constant is h, and if the photon has a frequency f, a color f, right? There's a certain amount of energy it can have, or in an oscillator, a spring oscillator 1/2 kx squared, that can only have certain energies that will change by a certain discrete amount. Energy is quantized. Not sure what I was really trying to say there. Let me pause a second. And in an atom, when an electron changes state, it can only change energy by, that means that it's got to either absorb or release a photon, so it's only got a discrete amount of energy that it can change by for an electron changing state. So that's sort of how we define the various states of the electrons in the atom. And the last thing, which is really what you get into in 302, of course, is this idea of the probability function. The fact that the electron really only has a certain probability of being in a certain place at a certain time, and this idea of the wave function, and that's where we now connect things to waves, that the probability is represented as a wave, and the fact that things are represented, that everything is represented by a probability or a wave, tells us that nothing is exact because you can't localize a wave like a particle, or when you look too close at a particle, it looks like a wave, and that has the uncertainty relations. Anyway, that really comes up. We introduced a lot of this in Intro to Quantum Mechanics, but it comes up in your next course, 302 Quantum Mechanics. Just remind you, the uncertainty relationship, you can't know both your position and velocity exactly. The better you know your position, the worse you know your velocity, and vice versa. But that's just sort of the end of Intro to Quantum Mechanics that leads to Quantum Mechanics, which is the next course. And that's pretty much a summary of the things in this course. And you should just do the homework, review the basic concepts, review the basic equations, and ask questions. Have a wonderful day.